the most promising combat rescue systems currently under investigation at the Naval Air Development Center, Warminster, Pennsylvania, is the Aircrew Escape Rescue Capability System, also known as AERCAB. Basically, the program is aimed at the development of an aircraft ejection seat system that in effect becomes a secondary short-range aircraft capable of an additional range of 50 miles from where it was ejected. Two versions are currently being investigated by the Navy, an autogyro technique shown here, and a sail wing concept. The experimental autogyro version is shown here in its stowed configuration, mounted on a wind tunnel test fixture. After ejection from the cockpit, deployment begins with extraction of the rotor from its stowed position behind the seat by a drogue parachute. The drogue force then pitches the seat rearwards to align the seat, rotor support arm, and folded rotor along the flight path. Aerodynamic force spins up the rotor. As rotational speed increases, centrifugal force extends the two-section, telescoped rotor blades to their full length, creating a 14-foot diameter rotor. The rotor now serves as a decelerator and stabilizing drogue. The system follows a retarded ballistic trajectory, slowing and pitching over toward vertical descent. The rotor support arm moves forward to its flight position, and the engine and tail surfaces are deployed. Operational deployment will be with a pyrotechnic device at a much faster rate. The engine will be a 270-pound thrust turbofan. The compressor of an existing engine must be reworked, and an aft fan must be added to achieve the thrust required with an engine size which will fit in the cockpit space available. Flight control will be by direct tilt of the rotor and weathercocking of the vertical tail surfaces. The full-scale model was tested in the 40 by 80-foot wind tunnel at NASA's Ames Research Center. In this sequence, aerodynamic characteristics and spin-up of the rotor are being evaluated. Each phase of the deployment sequence was independently studied and demonstrated. The rotor blades and rotor support arm were deployed from their stowed position behind the seat to a trail position by a drogue parachute. The rotor in the trail position was spun up by aerodynamic forces and the parachute was separated. With the vehicle in its vertical descent attitude, the rotor support arm is moved to its final flight position and the engine and tail surfaces are deployed. The first manned flights of the autogyro AirCab were performed at Barnes Airport, Massachusetts in January 1972. Landing gear, support structure, and instrumentation, which will not be part of the final AirCab, were added to the experimental model to facilitate testing. Enough ground runs were first made to give the pilot the feel of the vehicle. Towed flight tests were then performed. The vehicle was towed by a 75-foot line attached to a pickup truck. The pilot exercised lateral control to move the AirCab toward either side of the runway and was able to position it in the center of the runway for landing. flight of the autogyro AirCAB was demonstrated. The Williams Research Corporation WR-19 engine used for flight has a maximum thrust of 400 pounds, which is greater than required. This engine is too large to be integrated into the aircraft cockpit, but it was used because of its availability. Engine thrust during flight was in the 225-pound thrust range. The vehicle became airborne at about 50 knots and accelerated to 75 knots during powered flight. The pilot reported that general handling characteristics of the AirCAB were quite similar to a fixed-wing aircraft. The prime contractor during investigation of the autogyro AirCAB has been Kaman Aerospace Corporation, Bloomfield, Connecticut. The Stratos division of Fairchild Corporation, Manhattan Beach, California, has been the prime contractor during the evaluation of the sailwing AirCAB. The wing is formed by a sailcloth covering stretched between a rigid leading edge wing spar and a trailing edge cable. Deployment of the wing spar without the fabric covering illustrates the operation of the wing mechanism. When the sailwing AirCAB is ejected from an aircraft, a drogue parachute will deploy to stabilize the man-seat combination and to decelerate it to the vehicle deployment velocity of 150 knots. In operation, the parachute force is used to convert the ejection seat into a sailwing aircraft. The tail boom is pulled out to form the fuselage of the vehicle, and the tail surfaces and wings are erected. The engine is cartridge started and the vehicle achieves a cruise velocity of 100 knots. A rate of climb of 1,000 feet per minute is required for AirCAB. The flight ceiling. At the end of the 50-mile flight, or at any desired time prior to that, the crewman is separated from the vehicle and descends to the ground by personal parachute. Actual deployment of the sailwing AirCAB is shown during laboratory tests of the experimental model, which was later used for extensive wind tunnel testing. The parachute force causes the tail boom and wings to pivot away from their stowed position behind the seat. The parachute force is then transferred to the end of the tail boom, which is stowed in 3 telescoping sections. As the tail boom is extended, cables within the boom operate mechanical linkages which spread the wing and tail surfaces. The 170-pound thrust turbojet engine is located under the seat. A nose cone is inflated to protect the crewman from the wind stream and to reduce the aerodynamic drag of the vehicle. Longitudinal flight control is achieved by varying the incidence angle of the horizontal stabilizers to vary the tail lift. Lateral control is accomplished with wing spoilers which are mounted on the leading edge wing spars and can be raised above the top surface of the wing to decrease lift. Deployment tests were also performed at the Naval Aerospace Recovery Facility, El Centro, California, with the full-scale experimental model of the sailwing AirCAB mounted on a flatbed truck. The truck velocity was 50 knots. A 12-foot parachute was used to provide the deployment force due to the reduced velocity during deployment. Following evaluation of deployment, helicopter tow tests were conducted to demonstrate the flight capability of the droned sailwing vehicle. The Naval Air Development Center has been designated by the Naval Air Systems Command as lead laboratory to coordinate the Navy's programs that are aimed at air search and rescue. Based on the data presented in this report, it is felt that the feasibility of using AirCAB in this context has been established.